Hey everyone, welcome to this explainer. Today we are going to architect the Siemens Simatic Pcs7 operator station. We're talking about taking a massive, often chaotic industrial plant and transforming it into a highly structured, totally intuitive digital dashboard. If you've ever wondered how the world's best control rooms operate without missing a single beat, well, you're definitely in the right place.
To pull this off, we're going to follow a pretty strict blueprint. First, foundations and system limits. Second, tools and project structure. Then, bridging data and systems, the compilation engine, the operator interface, and finally, security and safe validation. Let's get right to it.
Section 1. Foundations and System Limits.
Okay, before you start building anything, you absolutely have to understand the plot size and the physical realities of the plant you're dealing with. You actually have a few diverse ways to physically lay out your architecture. Whether you're setting up a massive multiple station layout handling up to 40 clients, or maybe you're going with a more streamlined flat architecture with no dedicated server-client split, figuring out that physical system topology is step number one. You've got to know the shape of your network before you even think about configuring a single tag.
And once that topology is set, you must respect the hard engineering boundaries. There are some incredibly strict caps here, like the hard limit of 12,000 process objects per OS server. You literally cannot ignore constraints like that. If you try to exceed these plot limits, your architecture will bottleneck and eventually it's just going to fail.
Section 2. Tools and Project Structure.
So, with our physical limits defined and respected, it's time to open up the engineering tool belt and establish our fundamental file framework. Your main hub for all of this is process visualization via WinCC Explorer. Think of this as the center of gravity for all your specialized tools. It connects the graphics designer, which is where you actually build the physical process pictures, directly with tools like the Picture Tree Manager and the User Administrator. The whole system basically revolves around this central core.
Now, when you're working in these tools, you need to know exactly where your materials are supposed to go. For instance, if you're bringing in custom graphics, they have to go into the GRATS or Graphics Custom repository. It's really simple. If you don't drop your custom assets into this specific subfolder, they just won't be accessible across your broader project, period.
And it's absolutely crucial that you know exactly where that GRACS folder lives within the WinCC application path. This strict file architecture acts as the load-bearing walls of your entire project. It ensures that every single visual asset is sitting exactly where the system expects it to be when it finally comes time to render those screens for the operator.
Now, this next part is honestly one of the most genuinely brilliant features of PCS7. The software actually takes the physical plant hierarchy you've built in the Simatic Manager and it uses it to automatically generate the digital picture tree. But it doesn't stop there. It also automatically places and interconnects ready-made block icons right into your OS pictures for you. It basically acts as an automated blueprint, saving engineers just countless hours of manual drawing. It's a huge time saver.
Section 3. Bridging data and systems.
Right, so now that our framework and folders are set up, we need to run the plumbing. We have to connect the automation system, the AS, directly to the operator station, the OS. And to do this reliably, rather than relying on clunky, brittle default connection IDs, we use what's called a named connection. This symbolic name bridges the OS and AS over the plant bus and acts as a stable placeholder. This is a real game changer because it guarantees seamless redundancy failovers and simulation operations without ever breaking your vital tag paths.
This named connection is what carries your highly specific structure tags. If you break down the anatomy of one of these tags, it combines the plant folder names, the continuous function charts, the specific block name, and the exact I/O endpoint, all fused into one continuous, cohesive data string. Essentially, it tells the system exactly where every single piece of data is originating from.
But here's the catch, and it's probably the most critical constraint in this entire blueprint. 128. That is the absolute maximum character limit for a structure tag. If you nest your folders too deeply and your tag goes even one character over 128, your entire compilation process is going to crash. So you've got to keep it concise.
Section 4. The compilation engine. So we've laid the pipes, we've named our tags, now let's fire up the engine room that actually transforms that raw data into a usable operator dashboard. This all happens through the compilation wizard, which basically acts as your master translator. When you hit compile, it takes your input data and simultaneously processes 3 separate streams. It creates the tags, synthesizes localized messages and text, and finally it generates that structural picture tree and the block icons we were talking about earlier.
During this process, you're going to use the Compile OS Scope wizard. Think of this as your housekeeping step. You really have to define the scope here, making sure you delete old, orphaned automation system data before writing new tags and setting precise minimum acquisition cycles derived straight from the processing blocks. That is how you keep the whole system lean and lightning fast.
Section 5. The Operator Interface.
Okay, stepping out of the back-end engineering for a second, let's talk about the interior design, the actual interface the operator is going to rely on every single day. There's a crucial distinction here in how operators interact with the system. On one side, you have block icons. These are your high-level, at-a-glance dashboard indicators embedded directly into the plant visual. On the other side, you have faceplates. These are the detailed, separate pop-up windows that you open up when you actually need to change a set point or alter an operating state. When you single left-click a block icon, it opens the Advanced Process Library or APL faceplate. And notice how rigorously standardized this thing is. It's always divided into 4 distinct zones. Zone 1 for status, Zone 2 for operating modes, Zone 3 for values, and Zone 4 for views. This level of standardization is incredibly deliberate. It's designed to prevent cognitive overload for operators who are often working in extremely high-stress environments.
All of these icons and faceplates live on the operator canvas during OS runtime. And just like the faceplates, the canvas layout is strictly enforced. You get 3 specific areas: a fixed overview area at the top for alarms and navigation, a central working area for your actual process pictures, and a dedicated button area at the bottom. Because of this layout, the operator always knows exactly where to look.
Section 6. Security and Safe Validation.
All right, our structure is fully built and visually mapped. But before we just hand the keys over to the plant operators, we've got to lock the doors and test the fire alarms. Security here is completely non-negotiable. You have to configure authorization levels. For example, almost anyone might be given level 0 clearance just to monitor the process, but only specific personnel with level 5 can actually control it. And crucially, only those with level 6 clearance are allowed to alter critical systemic parameters, like limit thresholds.
So, with everything configured, completely secure, and seemingly ready to go, we're left with one massive, really high-stakes question. How do you actually validate this incredibly intricate architecture without accidentally crashing the active live plant servers?
Well, the golden rule is that you never, ever activate the OS runtime of an active server directly on your engineering station. The solution is OS simulation. This launches a totally isolated temporary testing copy. We've laid the topology, routed the data, built the canvas, and secured the perimeter. Because at the end of the day, a well-architected Pcs7 system doesn't just display data, it acts as the ultimate safeguard against operational disasters. So with all this incredible engineering power at your fingertips, what kind of system are you going to build? Thanks for joining me on this explainer.